Bismillahirrahmanirrahim. Today, inshallah, we are going to talk about determinants and its relation to the matrices, and then get back to chapter 2 to find the inverse of a matrix. Okay? So first, let's see what you know about determinants. Do you remember any application that you used determinant in before?
Evaluating the cross product.
Triple scalar, and cross product, and use determinants in Jacobian. Do you remember? In Jacobian. Actually, we used determinants before in many applications, such as cross product. If you have vector u and v, you want to find the cross product between two vectors. Do you remember the geometric meaning of the value of the perpendicular to the plane containing the two vectors? And the magnitude gives the area of the parallelogram. مش كده؟ Now, the u vectors like this, you can get the area of this parallelogram by getting the magnitude of the resultant vector. Okay. Well, triple scalar, lower u cross v dot w gives you a scalar, and this scalar represents the volume of this parallel pipe. Okay. I don't know if you know these determinants or not. To find the line passing through 2 points, if you know 2 points and you want to get the line passing through these 2 points, you can get the equation of the line by expanding this determinant. You'll get something multiplied by x, by y, and constant, and you can get directly the equation of the line by this determinant. And you have 3 points in the 3D space. You can get the equation of the plane containing the 3 points directly by expanding this determinant. You'll get something multiplied by x, y, and z, and constant by expanding this determinant. And if you want to find the equation of a circle passing through 3 points, not on the same line, you can get the equation of the circle this way. There are many applications on determinants. Actually, we are going to go through some of them. And this is the Jacobian. If you want to do substitution in several variables, if you remember, if you substitute x and y and z function of u, v, and w, you do some transformation, you get what is called the Jacobian. And it was something like this, if you remember, in multiple integral. Okay. What I am interested in linear algebra, we have some application on determinants. The first application is studying the unique solution case for the system AX equal B when A is a square matrix. Okay. So actually in this chapter, we are going to focus on square matrices only. So A is n by n, okay? And we want to study when this system has a unique solution. And if you know Cramer's rule, it is also based on solution of such a system, and its formulas are based on determinants. And to find what is called the matrix inverse of a matrix, you can find the inverse of a matrix based on the determinants also. And if you want to check the linear independence between vectors, suppose that I have 3 vectors in R3, V1, 2, 3, and I want to check if these vectors are linearly independent or not. Do you remember how to check? How to check 3 vectors are linearly independent?
هقدر اعمل simple equation C1 V1 plus C2 V2 لحد C B equal 0 ولا لا؟
بنشوف the solution of such an equation. If you have the trivial solution only, then the vectors are linearly independent. بالظبط. We have another way to find this. If you have number of vectors equal to the number of entries in the vectors, like 3 vectors in R3, you can check the independence using determinant. We will prove this, that if the determinant containing the 3 vectors equal to 0, then you can say that there is a linear dependence between the vectors. And in chapter 5, we are going to use determinants to find what is called the eigenvalues of a matrix. So these are some applications on determinants in linear algebra. Let's start with the first one, which is studying the unique solution of AX equal B when A is a square matrix. Let's start with a simple system. You have 2 equations and 2 unknowns, and I want to check when I'll get unique solution for this system. When we get a unique solution, if you can get after the reduction 2 pivots, right? So assume first that A11 is not 0, okay? Then you have a pivot for the first variable in the first equation. Okay, and I'm going to do the reduction to check if I can get a pivot for the second variable in the second equation or not. Okay, so first assume A11 equal to 0, not equal to 0. If A11 equal to 0, you can interchange the equations, right? If both are zeros, A11 and A21 are zeros, then you don't have a unique solution. Okay? So if A11 is not 0, so this would be my pivot, first pivot, and then do the elimination. So multiply by negative A21 over A11, the first equation, and add to the second one. After doing that I am going to scale the second equation to avoid the fraction A11. Multiply by A11, you will get this equation. So you can do it simply, the elimination step and the scaling step to get this echelon form. According to this echelon form, you'll get a unique solution if this guy is not 0, right? And this guy would be my second pivot. So I'll take this guy and I'll define this guy as the determinant of the matrix. So you will have a unique solution if this guy is not 0. Okay? This is for 2 by 2 case. So this guy, if you look at this guy, how to write this guy? If your matrix is A11, A12, A21, A22. So I'm going to define the determinant of the matrix. I write the matrix between vertical bars, and this is called the determinant of the matrix A. And I'll expand it as A11, A22 minus A12, A21. If this guy is not 0, then I'll get unique solution for the system, right? So this is the general matrix. We write, as you know, matrix between square brackets or rounded brackets. If you write vertical bars, you are talking about the determinant of the matrix. So the determinant is a scalar obtained from the matrix according to this expansion for 2 by 2 matrix. Okay? What if you have 3 by 3 matrix? I'm going to do the same procedure to guarantee that you have 3 pivots after reduction, and say that you will have, in this case, the unique solution. So I'll start by doing the reduction and take A11 as my pivot and do the same procedure. You can multiply the second row by A11 and the third row by A11 also, and then do the reduction to avoid fractions, actually. So you can then multiply the first row by negative A21 and add to the second row to do the elimination. And for the third row, I'm going to multiply the first row, the pivot row, by negative A31 and add to the third row. So we get something like this. Again, I want to reach the echelon form, so I want to eliminate which one? This guy, right? So I'm going to multiply this guy by a multiplier and add to the third row to eliminate this guy. After doing that, you get something here, and you want the something you get here to be a pivot. I'll take this guy outside. It would be something like this. As you see, it's very hard to remember such a thing to prove that the system has a unique solution, but actually this guy can be written as the determinant. So this guy actually is the determinant of the matrix 3 by 3. So how to write this guy? According to the expansion of the determinant. So I'll take the first entry, which is A11, multiplied by, I'm going to cover the row and column containing A11, and write the minor determinant remaining. Okay, so it will be A11 multiplied by this minor determinant, plus A12, move along the row. Okay, take the second entry, A12, I'm going to talk about the sign later, multiplied by the remaining minor determinant. And then A13, what I'm doing here is called expansion using the first row entries. So I'm going to take the first row entries, and for each guy I multiply the entry by a minor determinant. Okay? And here we have a sign. How to get this sign? Negative 1 power the sum of these guys, the sum of indices of the location or position of the entry. Here you will have A12 multiplied by negative 1 power 1 plus 2, which is actually positive, negative, positive, and so on. After expansion of this guy, you will get actually what you have in the third position for your pivot. So if this guy is not 0, then you will get a unique solution for your system. So to check if your system X equal B, when A is a square matrix, has a unique solution or not, you can check the determinant if it vanishes or not. If it vanishes, then you don't have a unique solution. So you'll have either an infinite number of solutions or no solution. But if the determinant is not 0, it means that you can get all your pivots, then you'll have a unique solution. Okay? So this is the first relation between determinant and matrices. So the determinant is a function defined on the matrix. You'll get a scalar value from the matrix, and this scalar indicates that you have either a unique solution or not for your system. Okay? لو determinant ب0 يبقى تبقى الكيس not unique solution, either infinite or no solution. عشان مش هقدر الاقي 3 pivots. لو n 3 by 3 يبقى مش هلاقي 3 pivots. في واحد هلاقيه 0 كده. If you find في اللوكيشن بتاع البيفوت 0, then you don't have a unique solution. مش كده؟ لا، هي هتقول لك unique or not. مش هتقول لك بقى not دي انهي واحده. دي لسه هنقول عليها. انا interested دلوقتي بالunique. Unique solution, you can know that you have a unique solution if the determinant is not 0. Okay? What happens for A if it is n by n? How to do the expansion? Let's get back to the 3 by 3 and try to generalize for n by n. So if you have A 3 by 3, I can write the determinant as A11, and the sign would be positive multiplied by the minor. I call the minor determinant of big A11. So this means the minor determinant after removing the entry, the row containing the entry of A11 and the column. Cover the row and column and write the minor determinant. This is A11. Then negative A12 minor of A12 plus and so on. Or negative, but the next one is negative and so on. So this is the case of 3 by 3, so we'll stop here actually for 3 by 3 matrices. But if you have n by n, يبقى في up to the last entry would be A1n minor A1n, right? And here the sign would be, I don't know according to the n, so I can write it as -1 power 1 plus n, the sum of these guys, right? Do you like the compact forms? I can write these guys in a compact form, summation forms, summation of -1 power 1 plus j, a1j minor a1j, j from 1 to n. Okay? So in compact form, you can write the determinant as the expansion of these guys. Summation -1 power 1 plus j, a1j minor a1j. So here actually I'm using the first row to expand the determinant. Actually the determinant has several properties that you can expand using any row and any column. So you can write the expansion this way, for example. Let's first take these guys together, -1 power 1 plus j times the determinant, and I'll call it the cofactor Cij in general. So Cij is -1 power I plus j times minor aij. So I'll take the sign with this minor together and I call it the cofactor. Okay? So instead of writing this expansion like this, I can write it as A11 times C11 plus A12 times C12 and so on up to C1n, A1n times C1n. So this guy actually contains the sign and the minor. So this guy is these two guys. And this one is this one. This guy is the -1 power n plus 1 multiplied by the determinant. Okay, so the cofactor contains both the minor determinant and the sign. Okay, this is called the cofactor of the entry ij. So you can, instead of writing this expansion this way, so you can write it simply as this one. So as I said, you can expand using any row and any column, the determinant. So we have another form here. Actually, what is written here is I'm taking actually row, which row? Row I. So we'll take the entry AI1 first, the first entry in row I, multiplied by its cofactor. So we will cover the row and column containing AI1 and write the remaining minor multiplied by the sign corresponding to the entry. And then move up to the last entry in row I. So this expansion is expansion using the ith row. Another property that you can expand using the jth column, for example. So I write the expansion as A1j. This is the first entry in row j, in column j, up to the nth entry in column j, and each guy multiplied by its cofactor. We'll see this in the example. And the sign actually is something like this: positive, negative, and so on. So let's do it for a numerical example. If I want to find the value of the determinant of this matrix. So if I want to use the first row, so I'll take the entry 3 and -2 and 0. And then multiply each guy of them, multiply it by the minor and the sign according to the sign rule. So the first one, you will have 3 multiplied by the minor. You cover the row and column and write the remaining minor determinant, which is 0, 1, 3, 0. And then the second term would be Positive or negative? The second term would be negative. Okay? So it would be minus -2 multiplied the minor, cover the row and column. So I prefer to use 2 pen to cover the row and column, and then a third pen to write. Okay. Multiplied by the minor, and then the third term 0 multiplied by its minor. Calculate these guys and get your final answer. So the determinant here equal to -5. So here I used expansion using the first row entries. Okay? According to the theorem, you can use any row or any column. So actually in this example, it's better to use which row or which column? The third column, because it contains many zeros. Okay? So I'm going to use the third column instead. If you want to use the third column, so the first entry would be 0, right? The second entry would be -1, and be careful, you have here negative sign, okay? Actually, the signs positive, negative, and so on. So you have -1, cover the row and column, and get the minor. Then the third entry term would be 0. So in this case, actually calculate this minor determinant to get the answer, and you get the value of your determinant. Okay? We have some properties for the determinant. First, if I want to find the determinant of A transpose, suppose that I have the determinant of A11, A12, A21, A22. So the determinant here is A11, A22 minus A12, A21. What if I take the transpose of this matrix? Do you remember the transpose? To change rows and columns. So we'll get A11, A12, A21, A22. What do we get? The same, مش كده? So actually we have the determinant of A transpose equal to the determinant of A. You can prove it for any dimension, 3 by 3, 4 by 4, and so on. Okay? So these guys are equivalent. I take the transpose of the matrix. We have another property if I want to find the determinant of a product of two square matrices. So suppose A and B of the same dimension, n by n, and we want to find the determinant of the product of two matrices. So if you are interested just in the determinant value of the product, you don't have to find the product first. We have actually a property says that this determinant equal to the product of the determinants. We'll prove this later, okay, using it in chapter 2. For now, you don't have to evaluate this guy. Don't multiply the matrices, simply find the determinant of each guy and then multiply the determinants. So for example, if you have this is A and this is B, and you want to find the determinant of AB. So you simply find the determinant of A, which is 1, determinant of B, which is 2. So the determinant of AB is 2. Instead of multiplying A by B, matrix multiplication, you will get this new matrix, and finding the determinant of this guy, which would be also 2. So it's simpler to use this property to find the determinant. Okay. What if I want to find the determinant of A raised to the power n for positive integer n? For example, if I want to find the determinant of A squared. So you can, according to this formula, you can find the determinant of A power 2. You don't have to find A squared first and then find its determinant. Okay? In general, if you have the determinant of a power n, you can find it as determinant a raised to the power n. Okay. What about the determinant of this matrix? 24. How to get this 24? You can expand using the first row. So we'll say 3 times the minor, which is this guy, and the determinant of this guy would be 2 by 4. So this is actually 3 by 2 by 4. So how can we write it as a property, the determinant of a triangular matrix equals to the product of its diagonal entries, right? What about this guy? This is diagonal, which is a special case of the triangular. So we'll get the same answer. So if you have a diagonal or triangular matrix, its determinant would be product of diagonal entries. Okay, look at this determinant and try to find the relation between the values of these determinants. What I did actually in the second determinant. Okay, we have interchanged the rows. مش كده? What about the value of each one? The first one is this guy. What about the second one? You will get A21, A12 minus A11, A22, which is the negative of this guy. So actually, if you interchange 2 rows, you will get negative the value of the determinant. So I have to put here negative sign. Okay? So I can write it here. If you interchange 2 rows, change the sign of the determinant. Actually, due to the property of the determinant, that determinant A equal determinant of A transpose, all the properties applied for the determinants are applied on either rows or columns. In determinants only, and be careful about this. For determinants, all the properties applied on rows or columns. However, in solution of system of equation, we apply only row operations. Okay, according to Gauss. Now, determinants, the properties applied on rows or columns. Okay, what about this determinant? Look at this determinant and see what I changed it from this one. What actually I did here, which is اللي هي الرو اوبريشن اللي كنا بنعملها اللي هي رو ريبليسمنت مش كده؟ فان انت عملت actually replacing للسكند رو you added k from the first row and replaced the second row. This is a Gauss operation for replacement when you do elimination. What about the value of the determinant here? Let's expand to find the value of the determinant. So we'll get A11 times A22 plus K A12 minus A12 times A21 okay. Can you cancel anything here? You have here K, A12, A11, K, A12, A11. So these guys are cancelled out. So we'll get actually A11, A22 minus A12, A21, which is the same as the determinant of this guy. So if you do the row replacement operation, it would not change the value of the determinant. Okay? You will get the value of the determinant as it is. You can generalize this, of course, for any n by n determinant. So actually, I'm trying to do the row operations and check how do these operations affect the value of the determinant. So we have actually 3 row operations, if you remember. row interchange. If you do any row interchange two rows, you will have to change the sign of the determinant. If you do the row replacement operation, it would not affect the value of the determinant. The third operation was row operation اللي هي scaling مش كده؟ scaling. تعال نشوف السكيلينج. If you scale a row by k, for example, what would be the relation between this guy and this one? Multiplied by k مش كده؟ If you expand, you will get k a11 a22 minus k a12 a21. So you'll get this value multiplied by k. So if you do row scaling, it would affect the determinant by multiplying its value by this k. Okay? And as I said, the operation applied on columns also for determinant. If you have, for example, this matrix A, its determinant would be 8 minus 6, which is 2. What about the determinant of 5A? You have here 5A. This is a scalar matrix multiplication. You multiply a matrix by scalar. So this scalar is multiplied by each entry of the matrix. Okay? So we'll get this matrix. What is the relation between the determinant of this guy and the determinant of A? Try to use this property. This property says that you can take k outside this row to write this formula. So for this example, you can take 5 again common between these guys to get this 2 and 6, and take 5 again from this row to get 1 and 4. So actually you'll take 5 from each row by applying the above property. This is from the first row and this is from the second row. So we'll get actually 5 squared times determinant of A. So can we generalize this property? If you have determinant, for example, of k, A, and A is n by n. What is the relation between this guy and the determinant of A? It would be k power n. Because actually k here is multiplied by each entry, so we'll find k multiplied by each entry. And from the properties of the determinant, you take k from each row, so we'll get k power n. ما هي الاكسبانشن اهي. يعني if you expand this guy, you will get k times the determinant of this guy. So actually as if you take k common from the entries of your row. So if you have here k, another k, you'll take k again from the second one. So actually if you expand, you'll get k squared instead of k. من البروبرتيز دي you can multiply, if you have this guy, you can multiply k by any row or any column. Okay, if I have this guy, I can write it as this one or this one. If you have this guy 5 squared, you can multiply the first row by 5 and then the second column by 5. The operation applied for any row or any column. Okay, let's take 2 minutes to find these guys quickly. They're using the properties, okay? Don't evaluate b squared or 2a or 2a transpose b. Just apply the properties to find these guys. First, you have to find the values of the determinants a and b using the row or column containing many zeros, and then find the values of the other determinants, okay? Which row or column do you prefer to find the determinant of A? the second column because it contains a lot of zeros, okay, which is 3, 0, 0. So first I write 3, positive or negative 3? Negative, right? When you do the signs here, move positive, negative, okay? So you'll take negative 3 multiplied by the minor, which is cover the row and column of 3. And then you'll get 1, 2, 3, 4, right? Which is negative 3 by 4 minus 6. What about B, determinant of B? Is it 1 by 5 by 5? This is not a triangular matrix, right? It's 1 by the minor. The minor is 5, 4, 8, 5, which is 25 minus 32. So what is the determinant of B square? It's the determinant of B power 2, which is 49. What about determinant of 2A? And A here is 3 by 3. It would be 2 power 3 multiplied by determinant of A, according to the property. So this would be 8 by 6. What about the last one, determinant 2A transpose B? Again, you have here scalar multiplied by matrix. And this matrix is 3 by 3 also. So it is 2 power 3 again. And determinant A transpose equal to determinant of A multiplied by determinant of B. Right? Okay. Can I multiply matrix 3 by 3 by matrix 2 by 2? That matrix multiplication. You have the multiplication to be valid first. I can't say that I want to find the determinant of A, B, and A is 3 by 3 and B is 2 by 2. This must be 3 by 3 for the multiplication to be valid, and then do the property. Determinant A times determinant B. So they have to be of the same dimension. آخر واحدة كأني أنا قلتها كده 2 times matrix, and this matrix is 3 by 3. So it is 2 power 3, the determinant of this matrix. And then determinant of A transpose times determinant of B. And determinant of A transpose is the same as determinant of A. Okay. Can you know when the determinant actually vanish? When if you have rows of zeros or column of zero, مش كده? If you have something like this, the determinant is directly 0. What else? في two columns similar, the same, multiple, same or multiple. Multiple or same, and A11, A12, K A11, K A12. Would this be 0? Let's expand. K A11 A12 minus K A11 A12, which is 0. صح؟ According to, if you get back to the property of row replacement, you can do row replacement. You can multiply the first row by negative K and add it to the second row. And this operation would not change the value of the determinant. Right? So this guy equal to, if you do this row operation, you will get 0, 0. Right? So the determinant would be directly 0. So if you find a row is a scalar multiple from another row, then the value of the determinant vanishes. What else? What about this one? بص كده. What happened here? The third row is MR1 plus KR2, which is a linear combination of the first and second rows. If you apply the row replacement, you can multiply this guy by negative M and add, and negative K and add, you will get a row of zeros. So the determinant vanishes. So actually, if these are vectors, and this vector is a linear combination of these guys, the determinant vanishes. So you can use this as a check for the dependence. So you'll have some relation between the vectors, so the determinant equal to 0. Okay? As you see, we use the determinant to check if the square system has a unique solution or not. If you have a value for the determinant, then you have a unique solution. And we can use it to check the dependence. If you have number of vectors equal to the number of entries of the vectors, so you can use it to check the dependence. However, the way we use to expand the determinant is not efficient practically for large dimension. So if you have, for example, 25 by 25 matrix, and I want to find its determinant using this way, it would be a big problem actually. This is a numerical note about this. The number of operation actually, number of multiplication you use for the expansion, using this expansion using the cofactor, takes n factorial multiplication. So for 25 by 25 matrix, the number of operation, as you see, 1.5 times 10 to the power 25 operation you need to find the determinant. So even if you have a powerful computer that perform 1 trillion multiplication per second, actually you don't have this in your PC, you have giga, okay? Giga operations per second. If you have trillion operations per second, you will need actually, if you divide this by 10 to the power 12, you will get 1.5 times 10 to the power 13 seconds. And if you divide this by 60 seconds, by 60 minutes, by 24 hours, by 365 days, you will need actually about 500,000 years to find the value of the determinant using the cofactor expansion. So this is very inefficient, okay, for practical use. So we need to find a better way to find the determinant for large system. Actually, 25 is very small on computer, 25 by 25 matrix. Okay, we can solve actually up to 1 million by 1 million and find the determinant in fraction of seconds. How عايزين better way to find the value of the determinant instead of using the cofactor. Based on the properties we said.
Using operation and simplifies the matrix of the determinant and evaluate by.
This is the key point. Actually, this is the key point. Try to use the reduction, okay, until you reach a triangular matrix and then find the value of the determinant of the triangular matrix. Okay? So let's take an example. If you have, for example, this simple matrix 3 by 3, and I want to find the value of the determinant. Let's apply the reduction, as Gauss said. So first eliminate these two by multiply the first row by -2 and add with the second. So this is the row operation, and this is the new matrix. What is the relation between the determinant of these guys? According to the properties, you did a row replacement, which does not affect the value of the determinant. So the determinant of this guy equal to the determinant of this guy. Let's continue. Try to take a pivot for the second variable in the second equation, but this guy is better to take it as a pivot, so I'm going to do interchange. So let's interchange the second and third row. What is the relation between the determinants? This determinant is the negative of this one, because you do one interchange. And let's next do elimination for these two. Multiply this guy by -2 and add with the third row until we reach this guy, which is in an echelon form, which is also an upper triangular matrix. So you can get the value of the determinant of this guy as 1 by 1 by 5. So the determinant of this guy is 5, and the determinant of this guy is -5, because I did here a row interchange for the second step. So this is U, upper triangular matrix, and determinant of A equal negative determinant of U. Okay? So we can write in general as a theorem here, if you have A reduced to row echelon form U by row replacement and R row interchanges. If I did R interchanges and row replacement operation. So what is the relation between determinant of A and determinant of U? -1 power R multiplied by U. So if you have one interchange, so you'll have negative determinant of U. If you did two interchanges, you will get the same as determinant of U. Yes? Yes. Yes. لو بسولف AX equal B يبقى السيستم ده يطلع له unique solution. No solution? I didn't write B to the right, the coefficient matrix. This is A. Put any B to the right and then do the operation on B and you get your solution using back substitution. I guarantee that I get the 3 pivots. So according to the problem, you can get an echelon form with all your pivots or not, right? According to the numbers you have in your matrix A. So you can get something like this or something like this, for example. If you get something like this, you get all your pivots, then determinant of U is not 0. And similarly, determinant of A is not 0 and you have unique solution. But if you get something like this, I couldn't find all my pivots. This is again the coefficient matrix, A only, okay? So here I have 3 pivots and I have actually 4 variables. Then the determinant of U equal to 0 because it's an upper triangular, but you have zeros on the diagonal, so the product of diagonal entries would be 0, okay? Numerically, if you compare this with the previous one, actually the number of multiplication would be proportional to this guy, 2n cubed power 3. This is much less than n factorial. For example, for 25, you will get around 10,000 operations instead of 10 to the power 25 operations in the previous one. So if you do actually, if your computer perform 1 trillion operations per second and you give you algorithm that needs 10,000 operations per second, it would be nothing. It would be in fraction in seconds. So on computer, you find actually the determinant using again the reduction. So the main point in these chapters is Gauss elimination and do the reduction till you reach the echelon form. It solves many many requirements in our problems: to find the dependence between vectors, to find the solution, unique, infinite, no solution, to check the uniqueness, to find the value of the determinant, and so on. All these guys can be obtained using reduction. Okay? Next lecture, inshallah, we're going to talk about how to get the inverse of the matrix using the determinants and using another method, Gauss-Jordan. Okay? Any question about this lecture? Thank you.